Hi everybody. I'm gonna try to clear up confusion that I had about the normal forces, the reaction forces. Um, while I was solving a physics problem, and it can also be it's the concept is equally important in statics or dynamics or any other branch of mechanics. It was a pretty nifty thing that I encountered while I was doing this question. The question is, let me just show you the question. Oops, here's my charging cord. I'm sorry about that. I'm making this video on my iPod. Well, so yeah, this is the question. There is a cart, and then there is a block on the cart, and it's an inclined plane, and the block will slide on the inclined plane because the friction here is 0. There is no friction on this surface, and th this is a pretty obvious problem on the face of it. But if you include this other part in the problem, then it seemed to me pretty that the problem easily got very difficult. The part that I'm talking about this is the surface. Now, in most of the problems, it's a fixed surface and it can't move and it's grounded and it just can't move. But in this question that I just saw a couple of days ago, this surface was frictionless and this card could move. Now, intuitively, I felt that if I were to slide on this surface instead of this block, then and there is no friction, there is 0 friction on the surface, then this card should move back. That was my intuition, but then I can represent it using the free body diagrams. The free body diagrams. That's a fancy name that we use in mechanics. But yeah, so this block has a weight W, and then there is a normal force that acts on it because of the surface, which is perpendicular to the surface. This is what I have learned. Normal force always acts perpendicular to the surface. And then there is this cart, and the weight of the cart is W2 maybe. This is W1, and because the surface supports the weight of the block, there must be another normal force acting in the upward direction on the cart. N2 maybe, and this N1. So these are two normal reactions. But if you have a look at it, then the forces acting on the cart are vertical, and they will balance each other out because there is no acceleration in the vertical direction. But the surprising thing here is that there is no force in the horizontal direction, no force at all. So why should the cart move? But well, my intuition says that the cart should move in the opposite direction. Now, what I was missing here is the concept of forces existing in pairs. Newton's third law. Newton's third law says that if there is a force, uh, which is the action force, then there must be another force, the reaction force, acting on another body in the opposite direction, given that the first action is acting on one body in one direction. So, what I was missing here is the reaction of this normal force N1. Now, this is how I analyze a problem when given to me. I first think of it as the possible forces acting on the body. Now, the most common forces that can act on a body are weight and the normal force. Now, normal force, I'm going to call it as contact force because that makes things real easy. Now, this contact force on this surface, the contact force is always given by the surface, and it's perpendicular surface. Now, the Newton's third law pair is, it goes as follows for this particular problem. You have weight, you have Earth down there that's pulling this cart with force equal to its weight, mg. That's one force. Now that's pair number one, the action. Then the reaction will be this cart trying to pull the Earth in the upward direction with the same force. Because the Earth is very big, this force doesn't really matter. It doesn't do anything because it's too massive. Now that's one pair. The other pair is weight of the block. W1. That's the force exerted by the Earth on the block in the downward direction, and there is an equivalent force acting on the Earth in the upward direction given by W1, and the first force given by W2. Now these are two forces acting on the Earth, and these are two forces acting on the cart. W2, oops, my bad, W2 and W1. Two forces. W1 on the block, W2 on the cart. So two action-reaction pairs are complete. For the second pair, however, I need, well, the second pair is the normal force. But the action force of the third pair, not the second pair, the third pair here is the normal force. That's the action force. The action that's given by the surface onto the block in the upward direction, the normal force. Now, there must be a reaction to that normal force. If that's the action, surface to the block, then there must be a reaction. Now, the reaction is the force given on the cart by the block, and it has to be in the opposite direction, acting on the other object, on a different object. So that's another force equivalent to N1, the same as N1, acting on the cart. Now that's a big thing. That's something that I didn't realize before. That was a force that I was missing. So that's N1 acting on the cart in that direction. A horizontal component of which will make the cart go in the intuitive direction, the direction that my intuition said the cart would go. So that direction. And as we are talking about this force, N2 is the normal force exerted by the ground on the cart. Now, as we are on the subject, we must not exclude the other part of the action-reaction pair. If this is the action, the force given by the surface to the cart, then there must be a reaction. That's the force given by the cart on the surface. Now, the surface being the Earth, there must be a normal force N2, same in magnitude, opposite in direction, on a different object, and 2 acting on the Earth. So this is the total action-reaction pair for this diagram. I know my handwriting is messy, but I'm really sorry about that, and this is my first video on YouTube, so I apologize for for my poor video making abilities, but these are the action-reaction pairs. N1 on the block by the cart, N1 on the cart by the block, N2 on the cart by the Earth, N2 on the Earth by the cart. And a component of N1, N1 horizontal maybe, is the force that's going to make the cart move in that direction. Okay? Alright, I hope this helped. And again, I'm sorry for my messy drawing. But yeah, so thank you.